Thank you everybody for joining. As I said, this is the March 2026 Impossible Metals webinar. I'm very excited to have Eric here. Eric is the CEO of Viridian Biometals, and they have been developing some really interesting mineral processing technology. And actually, Viridian started as part of Impossible Metals and spun out and is now a completely independent company. So let me hand over to Eric to give the presentation. We will take questions at the end, and please use the raise hand icon to get yourself into the queue, and then we'll take questions in order as they come. And as always, this webinar is recorded. It will be on YouTube next week. So thank you everybody for joining, and thank you Eric for agreeing to present, and over to you.
Good. Well, thanks for organizing this, and thanks to everyone who's joined. I imagine there may be people on the call who come from a wider range of backgrounds than most of my pitches are to funders and customers, but I know there may be people who are just curious about this field or people with environmental backgrounds. So I want to show some slides today and have a conversation on a sort of a broader range observation about what Viridian is doing, where the industry is headed. And yeah, I'd love to hear your questions after the slides. The metals industry is at least 10,000 years old. As long as there's any evidence that archaeologists have uncovered of civilization, there's evidence of people banging on rocks to get copper out of rocks, and you can see some of the physical artifacts of that in the lower part of the slide. And 8,000 years ago, once fire could be made hot enough, people discovered they could melt metal out of rocks. A few centuries ago, chemistry became well understood enough that acids and leaching became a common way to get metals out of rocks. And in 10,000 years, there have not been a whole lot of innovations in this field, and yet civilization's entirely dependent on having metals. So really interesting history. As long as the industry has existed, there have been people complaining about the metals industry. This is a nearly 4,000-year-old tablet. It's a customer complaint letter. This was discovered in ancient Babylonia, in now present-day Iraq. This is a letter from a guy who bought copper from a fellow. The complaint is the copper is of poor quality, and the buyer's servant was treated poorly upon picking up the copper. And I did a little more reading about this. Apparently, archaeologists have discovered the home of the copper salesman, and it's full of these tablets. He collected all of these customer complaints over, I'm sure, many years. But there have been concerns about the metals industry for millennia now. But let's look at what the industry looks like today, from extracting materials from the ground to getting metals. This is a really environmentally intense business. I have a series of photos here from Indonesia showing Indonesia is now the world's largest supplier of nickel, which is a metal used in batteries and also in steel making. And Indonesia provides about 3/4 of the world's nickel now. And step one to do that is to cut down the rainforest, as you can see on the top of the photo, and then scrape away the hillside where the nickel exists. This is not very high quality ore, meaning there's not a high percentage of nickel in it. So you have to take out a lot of land to get a certain amount of nickel. And it's done on a vast scale in Indonesia, and often right next to fishing villages like this one. And that's just step one. Step two, once you've extracted material from the ground, you need to get the metal out. That's also done in Indonesia in the nickel industry. This is a photo of a Chinese-funded processing plant in Indonesia. This is a very energy-intensive and toxic business. China has used very low-cost technologies to gain a market hold, but it is pretty horrific if you look at the environmental and social implications. In fact, right behind this processing plant, you can see rice fields. And one of the byproducts of this type of processing is toxic waste, often stored in lakes right next to the processing plant. So you can imagine in rice farming, which is also very water intensive, there's going to be a big environmental and health effect from doing the processing right next door. And, you know, if we continue on a business as usual basis, this is what things will look like. There is good news to share, though. The metals industry won't need to operate like this someday. And that's for a couple of different reasons. Firstly, if you look at what is driving the growth of the metals industry today, it's a growing demand for the metals, so-called critical minerals. These are the metals needed to make things that the modern world needs and wants, things like batteries and solar cells and wind turbines and electric cars and data centers, semiconductor chips. All of these things require special metals to be able to manufacture them. And the metals industry is responding to that. Now, since the industry got its start millennia ago, a lot of the easy stuff to mine has been picked over already. There used to be boulders full of copper just sitting on the surface in places like Michigan. All the easy stuff is gone now. So the industry has to look farther and farther around the planet for fresh ore. And what we're finding is over decades and centuries, the quality of the ore is declining, meaning there's less metal per acre in the ground than there used to be because the easy stuff has been gotten. So this problem drives up costs. It drives up the waste because you have to dig up more land to get the same amount of metal. So all of that is bringing focus to a couple of different sources of critical minerals. One is the waste from existing mine sites. If you look in the United States alone at active mine sites, they process all that is practical to process, but the waste product actually has $22 trillion worth of critical minerals remaining. That's more than enough to meet global demand for many years. I don't mean to trivialize this, though. That's a lot of metal just sitting in piles of waste. It is particularly difficult to get the remaining metal out. That's why it's waste, because conventional technologies have not been effective at getting the remaining metal out of the waste. There are a lot of companies now focused on that. And in fact, Viridian's technology can work very well in processing certain types of mine waste. So that's a new opportunity driven by the growing constraints in the main part of the industry of finding new places to mine. The other interesting place to look for critical minerals is in the deep ocean floor. And this is an issue getting a lot of attention and is somewhat controversial. But if you look at the bottom of the ocean, there are potato-sized rocks that just happen to be endowed with a lot of the metals that are on that critical minerals list. Things like copper and nickel and manganese and cobalt and rare earth elements are all in these rocks at the bottom of the ocean. And just between Hawaii and Mexico, that's the most intensely studied area in this field. There are $18 trillion worth of critical minerals sitting in these rocks. So the main point here is the supply of material is abundant if you can go get it, and if you have the technology to get the metal out of the rocks. The real choke point is in processing, and that's where Viridian comes in. That is, how do you extract the metals from the ore once you have the rocks? Now, as I mentioned, China has become dominant in this field. They now have about an 80% market share for critical minerals worldwide. And they've done that with low cost processing, but it's just too dirty and unsafe for the West, meaning Western companies are now struggling with this. If you tried to copy China, say in the United States, by building processing plants with this technology, you'd have to clean up the air pollution with scrubbers. You'd have to deal with the waste product in a more environmentally friendly way. You'd have to do things that drive the costs up, and therefore it's nearly impossible for Western companies to compete economically on the global scale with conventional technologies. And this is where Viridian can make a big difference. We're developing a way of extracting metals that unlocks this opportunity. With it's a low-cost technology that also it's quick and high performance, and maybe most importantly, it is clean. And all of those things allow this to be scaled in the West in the way you just couldn't with conventional technologies. Now, I want to talk more about how we're doing that. I'll do this later, but I did want to give you a hint here. We are harnessing a 1 billion-year-old technology. This is the way nature has evolved to extract metals from rocks. With bacteria that have evolved, they actually breathe the rock, and I'll talk more about what that means. But I have here a time-lapse video taken under microscope. The black blob in the middle of the screen, that is a small particle of manganese oxide, which is a very common type of ore around the planet, both on land and in the ocean. And I'll start the video now. You can see the rock, that particle is starting to shrink because bacteria are breathing it. And after 6 hours, it shrunk a little. This is zooming in more to a very small piece of that particle. The things moving around the particle are bacterium. They are swimming to the particle, breathing it, swimming away to get some food, and then swimming back to breathe again. And over a period of hours, you can see that particle shrinks. And after 12 hours, it's almost gone. After 18 hours, then that particle is almost completely dissolved. And that is the basis. This was sort of the aha moment for our founding scientist, who is a pioneer in this field of bacteria that breathe rocks. I'll talk more about what that means later, but I do want to talk about the business implications and other implications of it first. First of all, this process is relatively inexpensive. We have an economic model where if you look at the cost of our processing versus the very lowest cost in the world, which is a Chinese high-pressure acid leaching plant, like the type I showed you the photos of, we are 3 times more profitable, and we break even in 3 years, whereas a Chinese HPAL plant breaks even in about 5 years. The economics are really favorable, and if we compare ourselves to what could be done in Western countries, where the costs are higher to implement conventional technologies, then the economics of what we're doing are even more favorable. And the inherent benefit in economics is really driven by the inherent benefit we have in being clean and also simpler. And so what that looks like, if you look at a Viridian plant versus a conventional plant, both plants take in ore and put out metals, but look at the inputs and the outputs. We take in agricultural waste, which is abundant worldwide. Things like the waste product from yogurt making is actually food for our bacteria. So we need to give them food. We can work with ocean water or brackish water. And then we need some electricity to stir the tank and pump things in and out of the tank. The result is you get metal products and also benign waste. This is non-toxic waste. If the logistics are right, you can actually use this waste to put into bricks and cement and do something useful with them. Compare that to what happens in a conventional processing plant. The inputs are coal you have to burn in these Chinese plants to make heat and electricity. Acids, you either buy them or make them on site. Fresh water, this is a big constraint in a lot of locations and a big environmental concern as well. And also a lot more electricity than we need. And all of that goes into a plant that is more complex than ours. There are more steps that you have to go through to get from a rock to a sellable product. That complexity also increases the size of the plant. And at the output, you get metals, of course, metal products. You get a lot of air pollution, and you get toxic waste that is quite difficult to remediate. So that is generally just stored in ponds and as dry waste on site with no clear solution to the problem. Now, looking at our benefits, that we have economic advantage, we're simpler, we're cleaner. We want to take all of those benefits and use them to shrink the footprint of the plant. This is particularly important for a startup company like us. We need to generate revenue to make a difference in the world, and we need to do it much sooner than the metals industry is ordinarily able to operate at. So our solution to that is to take our benefits. We can shrink the plant size down because it's simpler, there's fewer parts in it, and because it's cleaner and cheaper, we can shrink all of that down to fit in a shipping container and still compete economically. This can't be done with conventional technologies. To shrink this size normally would drive the cost up too high to be able to compete. Not the case with us, and that containerization gives us some interesting advantages because we are building these processing plants in a box at a factory. We can test them there and make sure they're working, whereas with a full-size typical processing plant, you have to essentially design a custom plant and build it on site, often in a remote location, and it can take several years to get a plant like that running at full capacity, whereas ours will work much more quickly when you bring them on site. You can also bring containers pretty much anywhere in the world much more easily, even near a shipping port, which is especially important if you look at seabed nodules, because there will be ships coming to port with nodules on them. So co-locating with the port would be a big advantage. So where are we today? We're now working with 5 customers under non-disclosure agreement, and with 3 of them we've signed a memorandum of understanding, and we are scaling with them. All 5 of them have provided materials, and we're working with those materials in our lab. And interestingly for us, none of these customers currently has processing at scale yet. And that's a key risk for them as mining companies, and an opportunity for Viridian to show what we can do with an even footing with conventional technologies. And here's the scaling we're planning to go through over the next 2 to 3 years. We're currently working at 20 liters in our lab. And this is sort of the key metric. We need to get to much larger volumes to make a difference in the world, to be relevant in the mining industry. And so the next major milestone in scaling for us is to build a 10,000 liter pilot plant in 2 years. And then about a year after that, this demonstration plant, that will be of the size that's still small enough to fit in a shipping container, but will be about 6 times larger than the pilot plant. So that's where we are with scaling. And in terms of the core technology, we've already essentially proven that it's robust and tunable and flexible. We've made great progress, particularly in the last year or so. Where we began when we were still part of Impossible Metals, you can see the types of testing we were able to do and the results we were getting. These are 3 of the key metrics that we track. How much metal can we get out of the rock? How long does it take? And how large is the volume of the container where the bacteria are doing the work? And you can see on those first 2 metrics, on the recovery percentage and the extraction time, we're getting very close to where we aim to be for commercial operations now. 85% metals recovery in 2 days. We actually just got evidence in the lab that we're down to 1 day extraction time now. So we're making good progress there. And where we are farthest from where we need to be commercially is in the reactor volume. We've gone from just thumb-sized test tube experiments in the beginning, and we've scaled to 1 liter and now to 20 liters. And as I mentioned, we need to get up to 10,000 liters. That's pilot plant scale is large enough to show customers that there's essentially no more technology risk, that this is ready to go to market. And at 60,000 liters, that's the container size system that we think we can go to market with. Now, a little bit more about the science. This involves, about 20 or 30 years worth of microbiology, but it's really interesting stuff to point out that our bacteria are breathing the rock, not leaching the metals out. And the difference is in the respiratory process, whether people are breathing and eating or bacteria do it, it's pretty similar. When we take in food, when bacteria eat food, they take in electrons. The breathing process means they are getting rid of electrons, donating those electrons to something outside their own bodies. That's what breathing is. That's what bacteria do. And these particular bacteria have evolved in water environments that are largely depleted of oxygen. So they can't breathe oxygen. And the bacteria have learned instead to breathe metal oxides in rocks. Those are metal oxides are very common around the planet. And what that means is when the bacteria breathe, they actually have three small conductive wires that pierce their own bodies. They can swim up to a rock, press their wires against the rock, and that sort of completes the electrical circuit. It allows electrons to pass from the bacteria into the rock. And when a metal oxide absorbs that electron, it breaks the chemical bond between oxygen and metal. And that's how the rock dissolves. That's how the metal comes out of the rock. And that step replaces, in a conventional process, several steps that are very energy intensive and expensive. In our case, this reaction happens at ambient temperature, so there's no need to heat anything. There's no need to burn coal, for example, to boil a pot of anything. There's no toxic waste because this is not leaching. This is not an acidic process. And there's no need for fresh water. Our bacteria can thrive in seawater or brackish water. That's a major environmental benefit and a cost savings in comparison to conventional processing technology. Now, there are other ways of getting metals out of rocks, not just the conventional stuff that I described. There are a number of companies working on alternative methods. This is sort of a complicated chart. I thought about simplifying it, but really these four criteria, this is not just something we randomly pick for Viridian to look good. These are really the key metrics that enable us to scale the way a startup company needs to scale. And none of the other technologies meet all of these requirements. So we are in a better position to scale than any other technology that we're aware of. And that's in terms of cost. Of course, that's important. Complexity determines the physical size of the plant and ties into the cost. The speed is critical. You have to be able to get metals out quickly for this to make economic sense. And most of the others, for example, can do that, but not, for example, with heap leaching, with bio-leaching. There's some great companies working on this, but this bio-leaching can take months and even years to be effective. And so that disqualifies bio-leaching from working in the mainstream industry and disqualifies it from being shrinkable and therefore scalable in a business sense. And finally, the environmental footprint. If you're producing toxic waste, no matter how small you can make the plant, you're producing huge volumes of toxic waste, and that becomes an inhibitor on scaling. So this is why we think Viridian is well positioned to scale, and particularly in comparison to the other ways of getting metal out of rocks. And I think this is my last slide. I just want to emphasize the potentially transformational benefits of what we're doing. Obviously, low cost is a good thing, but if you dig a little bit deeper into what low cost implies, with conventional technologies, as I mentioned, in a Western country, really the only way to compete on a global scale is to depend on government subsidies or tariffs. And that can make business decisions really quite challenging when the policy and tariff regime changes from presidency to presidency, or even week to week, like we've seen recently. It's very hard for businesses to know where to build a plant. Can they depend on that policy regime existing by the time the plant is up and running? You don't need to be so concerned about that with Viridian, because we can compete on our own merits without any of those tariffs or subsidies. And so that's a follow-on benefit of being low cost. Another interesting aspect is all the environmental benefits I mentioned. From a business standpoint, that can accelerate deployment time, meaning the time to go through regulatory scrutiny and legal challenges. It will be simpler and faster and cheaper because of our environmental benefits. And then finally, building these small containerized plants, it creates a nimbleness that opens new markets and new locations that are just not viable with conventional plants. And that is the end of the presentation. Yeah, that's my last slide. I'm happy to take questions.
So thank you, Eric. This was a fascinating presentation. I really liked the history lesson as well, and the customer complaints from 4,000 years ago. Fascinating. So anybody that would like to ask a question, please use the raise hand icon, which is at the bottom of the window, 2 icons left of the red hang up, and that will put you in the queue, and then you can unmute yourself and just ask your question. Whilst we're waiting for some questions, maybe Eric, I'll ask you a question.
Sure.
What are other people considering for seabed nodules for processing? What is the current processing that people are looking at?
Yeah, good. I'm glad you asked that question. What we've found, we've talked to a number of seabed mining companies, and every one of them I've been able to talk with is putting some of their own resources into at least exploring the processing options. This is a critical issue for seabed mining companies. And what we're finding is they're all working with consultants or doing some in-house work to figure out what combination of known conventional steps can be used to take a seabed nodule and produce sellable products from it. And I haven't so far seen anything particularly novel in what other companies are able to do. It's not a main focus. Their main focus is just how to harvest the nodules, but they need to know that somebody will be processing the nodules. And Oliver, I'm glad you asked that question, because I forgot to mention that one of the things we're now doing, we've sensed this void in the marketplace. There is no processing company that has stepped in and said, we will become a processor of seabed nodules. It's still a little early for a big company to do that. But for Viridian, we are now working to put together a consortium of seabed mining companies, because we see them all exploring this issue of processing. They're probably all doing pretty similar work if they were able to compare notes, and there's not anything we've seen that's particularly innovative in it. And we want to become the processor of record for seabed nodules and at least offer an alternative to these conventional technologies. We know we have a lot to prove in terms of our scale and the newness and craziness of what we're doing, but we think that's a great combination. I personally think that harvesting seabed nodules would be a whole lot cleaner than doing what we're doing on land in places like Indonesia. And if you can combine that with the what we think is the cleanest way of extracting the metals from the nodules, it's a great combination.
Great, thank you for that. Let's go to questions. Reminder to have people, please just use the raise hand icon. I see a couple of people in the queue. Kieran, over to you. Please unmute and ask your question.
Thank you, Oliver. Can you hear me? Yeah.
Yes.
Wonderful, thank you. Thanks, Eric. This is very educative as well as fascinating presentation. Two things came to my mind. Number one, in the selection of the bacteria, did you use any genetics of, means for a particular metal? Do you need a particular kind of bacteria? That was the first question. And the second one was in one of the slides, I believe it was slide number 13, there was a mention that you need to use electricity. And what exactly electricity's role is in this particular process?
Okay,
Thank
yeah,
you.
good. Thanks for the questions. On that first one, I think we are fortunate that we are harnessing nature. So we're not synthesizing brand new bacteria. They exist in nature. In fact, we've sampled wherever we've been able to sample an environment where there should be bacteria that can breathe rocks, we actually have found bacteria that can breathe rocks. So we now have a library of about 35 bacterial strains that can do this with rocks. And when a customer sends us a new material that we haven't worked with before, we need to do a bunch of small scale tests in parallel. We make some educated guesses about which bacteria will work best. It's often a combination of bacteria that turns out to be optimal for a particular material. And getting to the heart of your question, we do have tools with our team to be able to manipulate the genetic structure of the bacteria, but we've only needed to do that on a limited basis. In fact, bacteria replicate so quickly. If the bacteria are happy, they reproduce every 20 or 30 minutes. And so the rate of mutation is much, much higher than it is, say, for people. And we find nature sort of solves this problem. If you introduce bacteria to a new rock, the bacteria will quickly evolve all on their own to optimize for that particular rock. So we can nudge it along with modern tools of microbiology, but we like to start with nature and harness it from there. And on your second question about the electricity use, that's mainly the main use of electricity in our case is really just to stir the tank. You can imagine you've got a tank full of mostly ocean water, and then we put in crushed ore, and you add bacteria and food. Now, if you just let it sit, the ore particles will tend to sink to the bottom, and that can make it more difficult for the bacteria to breathe all of those particles. We need to suspend those particles in the tank, and that's where most of the electricity goes, just to circulate material in the tank.
Thank you. That's fascinating. Thank you.
Yeah, so reminder, if other people have questions, please use the raise hand icon. John, over to you. Please unmute.
Yeah, good morning. It's certainly a pleasure to see you all again, Holly and Oliver. It's good to see you again, Eric. I don't think we've spoken before, but I'm sitting here in Pongo Pongo, American Samoa. A couple of points I'd like to make is the MV Ocean Guardian and MV Armada 8605, two high-tech survey vessels are on station right now surveying the seabed mineral resources of the American Samoa, EEZ. So, you know, Eric, I listened carefully to what you said about your timeline as far as when you will be able to develop a pilot program. And maybe the question or the statement I'd like to share with you this morning is that we cordially invite you to make American Samoa part of your home. We're pretty much right in the field of the seabed minerals that are encumbered in your process. So that's item number one. Item number two is we have a fine young group of young graduates in biology and chemistry that are here on island that can facilitate your startup program and eventually become manager supervisors in your program. So finally, the question is, after we've extended this invitation, to Viridian to make American Samoa part of their home is, I wonder if you could go again over your timeline as toward when you would get to pilot status. And I know looking down the road a little bit, but that's okay. Maybe a timeline and when you actually expect to become commercially viable. Thank you.
Mhm. Well, thanks for all of that. And John, American Samoa is a really interesting case for a number of reasons in this field of critical minerals. As you pointed out, there are probably trillions of seabed nodules just within the exclusive economic zone of American Samoa. It's also not that far from the Cook Islands, and at least in a global sense. And so the nodules are there. Interestingly, you know, in a small island setting, I don't think conventional processing would be viable. So if American Samoa were to become active in harvesting seabed nodules, you'd face a problem that I know there are people that grow up in places like American Samoa, and if they want a good paying job, they often have to leave the island to go somewhere else to work. And that's kind of a loss for the culture and community. There's a possibility with Viridian's technology that you could do processing on the island. And that's for a variety of reasons. First of all, because it's clean, you don't have to store toxic waste somewhere. That's an even more pronounced problem for a small island nation. Also, it's much less energy intensive, so you don't need an enormous supply of electricity to make the processing work. And as I mentioned before, if we can shrink this down into a container-sized plant, and that's what we're showing here, this 3-year plan you asked about our timing would be to produce the first demonstration plant. This would be a plant that fits in a 40-foot shipping container and will be commercially viable. So the only constraint after that, after we show the first one, I expect will be supply limited. We'll need to build as many of these as we can quickly and bring them to where customers want. And I'm excited for the possibility at American Samoa. You could actually create good jobs in a clean technology with Viridian, and it would bring the economy of American Samoa higher up on the food chain, so to speak, in the mining industry. Rather than just exporting your raw material, you could do the processing there and keep more of the value of those metals in American Samoa.
Great. So the next question is JV. Please, could you unmute and ask your question?
Hello. Hello. Good morning. Can you hear me?
Yes.
Yes.
Yes. Thank you. Good morning. I'm JV from Pacific Island Times and in Guam. I just need some clarification. Based on your presentation, I understand that Viridian Metals will be more on the processing side. Once the rocks are already harvested, they will not be involved in the actual mining and digging up of the rocks from the bottom of the sea, right? So
that's right.
Is that like because based on I think your parent company, Impossible Metals, has expressed interest in American Samoa and possibly in the CNMI, in the Northern Mariana Islands. Will they be the one doing that?
Well, good questions. First of all, I want to clarify. You said parent company. We did start out as a project at Impossible Metals, but Viridian is entirely independent now. We're an independent startup company. We're not directly connected to Impossible Metals. However, I personally love what that company is doing. If you look at the different ways to harvest seabed nodules, there are a lot of other companies developing dredging equipment to do that, whereas Impossible Metals is developing robot arms with AI and cameras to pick up nodules individually. I'm not here to plug Impossible Metals. Oliver is very good at that, but I like what they're doing. And At any rate, yes, Viridian is not in the business of harvesting the nodules. We're actually agnostic. We can work with a lot of different materials. We can work with materials from land-based mining. We can work with mine tailings, as I mentioned. We have the most experience working with seabed nodules because that's where we got our start. So we're getting very good results on seabed nodules, but we're not planning to harvest them ourselves.
I see. Thank you very much.
Thank you.
Don't see any other questions, so maybe I'll ask one more, but just a reminder, please use the raise hand icon and ask any questions that you might have. Eric, talk a little bit about your IP position. How do you defend the business, etc.?
Yeah, good. We do have a patent filing. We've filed in the US, we've filed in several other countries where mining is a big industry. As any of you who have filed patents before and gone through the process, it takes a long time, and it's taken some years, but just now the patent office has started to review and take action on our patent. And it looks very encouraging from where we are in the review process. And if that patent is issued, we've got some very strong intellectual property in our claims in that patent. It's essentially going to block anyone else, anyone who would want to use bacteria that breathe rocks and apply them to extracting metals would be infringing on our patent. So we think it creates a very strong position in intellectual property. Beyond what's in patents, though, we've developed a whole lot of knowledge that we keep as trade secrets about how to optimize. I mentioned all of the different bacteria strains we have worked with that can extract metals. How to optimize the formula for a particular material is something we've gotten quite good at. We've systematized the process, and even if someone were to try to copy what we're doing, which would probably infringe the patent, I think they're quite a few years behind where we are now.
Thank you. Kieran, please go ahead, unmute yourself, and again, please raise your hand, anyone else that wants to ask questions.
Thank you, Oliver. Eric, correct me if I am wrong, but for these seabed mining nodules, you will have to grind them to a size of your interest, right? And that is going to require a lot of energy, and then you will put it in your reactor. Is it right? Or you have to just put the whole rock and then let the bacteria do the job?
Well, the short answer is yes, grinding would be step number one. And you're right, that does take a lot of energy. We actually have an advantage there. So I'm glad you asked this question. First of all, seabed nodules are, they don't take a lot of energy to grind and crush, unlike some other materials on land. This is fairly soft material, so it doesn't take a whole lot of energy. The other interesting thing, grinding is step one in any processing technology I'm aware of, conventional or otherwise. You grind the rock. And I'll digress here for a moment. Our bacteria could work with a whole seabed nodule. It would just take them longer. The surface area is not as large. It would take longer for the bacteria to dissolve that rock if you don't crush it first. So the reason we crush is to accelerate the process. The second point I want to make is that with our technology, it's not necessary to crush to the very small size that's necessary with conventional processing. If you look at conventional processing, they have to crush typically to maybe 20 microns or 50 microns average particle size. That's to maximize surface area and increase the chance of a random encounter of a little particle of ore with a leaching agent like an acid. So they crush to a very small size. With our technology, it's not necessary to crush to such a small size. In fact, our particles can be 10 times larger than that. And what we found is we're essentially harnessing the intelligence of bacteria. They can identify rocks that they can breathe. They can swim to those rocks. They can share that information with their friends. And so we don't need to crush to such a small size. And in doing that, we can save a lot of energy in the crushing step. It's really interesting stuff. And I'll also point out, bacteria do all of that thinking, figuring out where they can breathe, swimming there, sharing that information with the friends. They can do all that even though they don't have a brain. This is a one-cell organism with no brain, and yet it's fascinating stuff. And I digress, but I think I answered your question.
Thank you. Wonderful. Yeah.
Javine, please unmute and ask your question.
Thank you. One of the biggest issues in Guam and the Northern Mariana Islands is the potential for revenue, and there is a possibility that they may not earn anything from this because the mining will happen in international waters outside of the EEZ. So is that, one of the things you mentioned is like, because this is a smaller kind of plant, you can actually locate it in can you locate it in Guam or in the Sinamite to make sure that they also earn some money?
Yeah, that's right. And if I could, I'd like to back up there. If you look at Guam's exclusive economic zone around the ocean, there's a piece of it, I believe, in the northern end of your economic zone. It overlaps with what's called the Western Pacific Nodule Basin. I think that's the name. Anyway, there's a large flat plain at the ocean floor where there are trillions of nodules, and that area overlaps with Guam's exclusive economic zone. And so there is some economic opportunity for Guam if you can partner with seabed mining companies. You have a lot of nodules in your economic zone. And so that's the first thing I wanted to mention. But yes, to your question then, it's the same with American Samoa. I think if Guam wants to get higher up on the economic food chain, so to speak, not just exporting raw ore, but processing the ore so that you gain the benefit of producing metals rather than just producing the rocks. I think that would be very difficult to do using conventional processing technology. It's too big, it's too energy intensive, it's too toxic to make sense on an island nation. But with Viridian, because we have these inherent advantages in our technology, we can shrink the size of the plant down to a container. We are much less energy intensive, so you don't need to produce as much electricity to run the plant. There's no toxic waste, so you don't have to be, you still have waste. There is a waste product. Everything in the rock other than the metal is left over. You need to put that somewhere and do something with it. But the fact that it's not toxic makes it much easier to manage, particularly in an island nation.
Okay, thank you very much.
Marcus, please unmute yourself.
Yes, thank you, Eric, for your presentation. I'm wondering regarding the bacteria. You mentioned that they are anaerobic, and I'm wondering how you would maintain a environment in the processing plant that would still be anaerobic or oxygen-free. Thank you.
Good. Yeah, it's an interesting feature, a key feature in these bacteria. They actually can breathe oxygen. It's just they have this extra tool in their kit to be able to breathe when there isn't any oxygen to breathe. That's when they breathe the metal oxides. So maintaining, if you imagine if you have a tank, a bioreactor, it's actually not very difficult to create an anaerobic environment, just to fill it with seawater, and you could sparge out the remaining oxygen. But in the case of our bacteria, it's not even necessary to take that stuff. The bacteria will breathe all of the oxygen that can be breathed in that environment until there isn't any oxygen remaining. and then the bacteria will switch to breathing the rocks. So we're just creating the environment where the bacteria can thrive, and it's not very difficult to create that anaerobic environment.
So do we have any final questions? We have a few more minutes left. Maybe I will ask another question, and again, please raise your hand if you'd like. So Eric, talk a little bit about your business model. How do you intend to commercialize this technology?
Well, good. I think the key for us right now is in scaling, because the other metrics that we're tracking, as I showed on another slide, are we're getting really good performance now. So we absolutely must scale, as this chart I'm showing now points. That's where our business model right now involves partnering with customers, getting material that we can work with so that we can scale, and also raising enough money to be able to scale like this, to buy the equipment, to have the partners that can accelerate our scaling with us. And then ultimately, once we've gotten up to this demo plant scale, this will be a profitable plant. This is when we can start generating meaningful revenue. And interestingly, for a startup company, most of the funding we can raise right now is from venture funders and angel funders. After we show that the technology has been de-risked and we're building these demo plants, I think we can then switch to what's called project financing. And that means mining companies and other partners will partner with us to build more of these plants. We probably won't need to raise more venture capital at that stage, and we'll be generating revenue in partnership with customers once we get up to this demo plant scale. I think that answers your question.
Yeah, great. Well, I think we should wrap up there unless there's any final questions. If not, I want to thank Eric. Fascinating presentation. If people want to get in touch with you, how's the best way?
Yeah, please. And I've really appreciated the questions today. My email is at the bottom, eric@viridianbiometals.com. You're welcome to write to me. And I really do, whoever's on the call, if you're an investor, we'd love to talk. If you're a customer, we'd love to talk. And if you're an environmentalist, we've got a lot to talk about. And so please do feel free to write to me if you'd like to continue the conversation. And thank you all for your time.
Yep. Thank you, everybody. We will publish this next week. It will be on YouTube, and we look forward to seeing you at our next webinar. So thank you again.
Thank you.
We'll sign
Thank
off.
you, everybody. And I will just do a little commercial. We have Justin Manley coming next month, April 17th. And his presentation will be Trends in Marine Robotics, Defense, and Dual-Use Drivers of a Dynamic Industry. So I will send the registration link out when I send out the link to this webinar on YouTube. So we look forward to seeing you next month too.
Thank you. Bye.
Thanks, everybody.